a class A emitter follower bias using the circuit shown in figure 12.2 uses VCC to VCC equal to 10 voltage, R is equal to RL, which is equal to 1 kilo ohm resistance, with all transistors including Q3 identical. Assume VB to be 0.7 voltage. What are the upper, okay, VB is equal to 0.7 voltage, and also VCE saturation is equal to 0.3 voltage, and beta is to be very large. For linear operation, what are the upper and lower limits of output voltage and corresponding inputs? How do these values change if the emitter base junction area of Q3 is made twice as big as that of Q2 and half as big? Okay, now let's look at all the situations. First, let's look at this situation. For linear operation, what is the upper and lower limit of the output voltages? So we have to find out the V0 max and V0 minimum for this one. In order to find out the V0 max, we have to use this equation, that is V0 max is V0, or you can say V output, VO max, which is equal to VCC minus VCEsat, that is VC saturation, and VCC is known 10 voltage. Plug that one in, and then VC saturation also known, that is 0.3 voltage. So if you calculate this one, you are going to end up getting 9.7 voltage, and this is our V0 max. Now in this case, when V0 max, what's the input voltage? In order to calculate this one, we have to use this equation. VO is equal to VI minus VBE, and we are interested in input voltage. So if you rearrange this equation, this is going to be VO plus VBE, and VO we just calculated that one to be 9.7 voltage, and VBE is 0.7. So plug that one right here, and that's going to give us 10.4 voltage, and this is our V input. Okay, now we have to find out the V input when the output is minimum. So in order to do that, in order to calculate that, we have to look at, first we have to know the current, because V0 minimum can be calculated using this formula, negative I times RL. We know the load resistance, that is RL, that is given in the question, that is 1 kilo ohm, but we don't know what's the current right here. But we can calculate the current by looking at the, we can look at this loop right here. Here we have ground, and here we have VCC, and here in the Q2 we have a VBE. So all the, like if we combine all the voltages divided by the resistance, that's going to be the current flowing through this. So here this voltage is 0, so we can say I is nothing but I is equal to 0, that is ground, minus this voltage plus this voltage, that is, this is VBE, and this voltage right here, that is minus VCE, plus minus VCE, that is equal to minus VCE. So you can just write it like this. Okay, and if we calculate this one, we are going to have this one 0, and here we have negative, and then VB is 0.7, and then VC is 10. Okay, this one is VCC, not VCE. VCC is 10 provided right here. Plug that one right here. So here we are going to get 0.7 minus 10, that's going to be negative 9.3. Negative, negative, make it to positive. So we are going to have positive 9, and also this one should be divided by the resistor in between. That is, in this case, that's a RL, and RL is equal to R. So you can put R as well, RO, RL, both of them, right? And R is 1K. So you end up getting 9.3 divided by 1K, and that is equal to 9.3 milliampere. And this is the current we have. Now since we have the current, we can calculate the V0 minimum. V0 minimum is nothing but negative I times RL, and we know that I is 9.3 milli, and we know the load resistance is 1 kilo ohm resistance. Kilo and milli cancels each other, so we will end up getting negative 9.3 voltage. Okay, this is the minimum voltage. And there's also another equation for minimum voltage. We had to use both of them and we had to compare which one to choose. So in this case, and we had to choose the one close to zero. So here there's another output minimum equation is given by absolute value negative VCC plus VCEsat divided by RL times RL. Okay, and here absolute value negative 10 plus VCEsat is given to us, that is 0.3. Right here RL cancel, so we can neglect that. So this is gonna be, and also negative in front here. So this is gonna be we are gonna end up having negative 9.7, and that is absolute value, so that's positive 9.7. But outside we have negative, so that's gonna make this one a negative 9.7 at the end. So we have to compare this one and which one is close to zero. In this case 9.3 is the one that is close to zero, so we have to choose that one. And we choose that one for what? We choose that one to calculate the input voltage. Input voltage equation is exactly this: V output is equal to Vi minus VBE. We use that one again here. V output is equal to Vi minus VBE. We are interested in input voltage, so we rearrange this equation. It's going to be V out plus VBE, and here we are going to have V out to be the one close to zero, that is negative 9.3. This one is a little bit away, so this is the one we have to choose. We choose negative 9.7 for the 9.3 for this, and then VB we know 0.7, and that comes out to be negative 8.6 voltage. And this is the input voltage when the output is minimum. So we have, when the output is maximum, the input voltage is 10.4. When the output is minimum, the input voltage is negative 8.6. okay, this is the first case. And the second case we have is, how do these values change if the emitter base junction area of Q3 is made twice as big as the Q2? Okay, if the area is twice as big, the new current will be changing. So the area is going to only affect the current. The new current will be, if the area is doubled, then the new current is going to be I divided by 2. Okay, so this one doesn't affect the VO max equation, like V input when the VO max, because for the VO max we have to use this equation, VCC minus VCEsat, and we calculate this Vi minus VB. So we use all this. There's nothing related to current. But when we use V0 minimum, that's the only thing that's gonna affect this. Okay, so we can directly say for this one the V0 max is exactly the same thing. You can write all of them, and you will end up having the V0 max to be 9.7 voltage. Therefore V input is going to be 10.4 voltage. Okay, because for the V output max, it doesn't affect, the current doesn't affect anything. but for the V0 min it's gonna affect, because for the V0 min we had to use this equation, that is negative I times RL. Now in this case the I is I divided by 2, so the new I is going to be I divided by 2, which is the previous I we calculated 9.3 milli, that one divided by 2, 9.3 milli divided by 2 times 1k, RL is 1k, and milli kilo cancels, so we will end up having 9.3 that is divided by 2, that is equivalent to negative 4.65 voltage. And we have to use the other equation as well, this one. Okay, and this equation gonna exactly use the same answer, because there's nothing changing here, there's nothing related to current, so exact same value, exact equation. So the V0 minimum in this case is negative 9.7 in the other equation. And when you compare both of them, which one is close to 0, that is this one in this case. So we have to choose this one to calculate the input voltage. So input voltage, to calculate the input voltage, we use this equation: V out is equal to Vi minus VBE. Therefore Vi is equal to VO plus VBE, and in this case the V output is negative 4.65 plus VBE is 0.7, and if you calculate that, you get the input voltage to be negative 3.95 voltage. Okay, this is the input voltage when V0 minimum. So we calculated the input voltage when the V0 max, when the area is doubled, that is 10.4 voltage, and VI when the V0 minimum, that is when the area is doubled, that is negative 3.95 voltage. Okay, and also there's one more part, that is if it's half as big. So if the area is halved, what's going to happen? If the area is halved, then what's going to happen is now the I new is going to be 2 times I. Okay, again VO max doesn't get affected by this, because there's nothing related to current in the VO max. So this is exactly because VO max, we use this equation, we find the input voltage using this, so there's nothing related to current, so it's going to be exact same thing. VO max is going to be equal to 9.7 voltage, therefore V input is going to be equal to 10.4 voltage. But V0 minimum going to be affected, because V0 minimum is nothing but negative, this one, negative I times RL. And here the new current is going to be 2 times the current of I we found out before. The I we solved before is 9.3 milli, and that's going to be double right now, multiply by 2, and then RL is 1k ohm resistance. Milli kilo cancels, 9.3 times 2 is 18.6, so this is going to be milli and kilo cancels, and negative 8.6 voltage. And V0 minimum other equation, there's another equation we have to use, is that is this. That's going to be exact same thing, because there's nothing related to current, so it's going to be exactly this, and when you calculate, you're going to get negative 9.7. Now we have to look at in these two which one is close to 0, and in this case this is the one, so we have to choose this one and apply in this equation. V0 is equal to Vi minus VBE, and therefore Vi is going to be equal to V0 plus VBE, and V output is nothing but negative 9.7, and VBE is 0.7, and that comes out to be negative 9 voltage, and that's the input voltage when the V0 minimum. Okay, and that's it for this video. I hope you guys found this video helpful. Thanks for watching. Don't forget to subscribe my channel. See you guys on my next